Hey guys, this is Dr. Rodham. Welcome to class today. I guess you got an email from me that describes some changes we're making to the class to try to handle the current coronavirus situation. And so one of the things we're going to do is we're going to drop some topics from the end of the course. There's some testing topics that we normally teach at the end of this course, and those topics have been moved to other classes anyway. And so this semester we're going to take advantage of that and just kind of drop them out. So any of the testing related topics we're not going to cover. So basically all we're going to do in the class is finish out the Android programming part, and then we're just going to review for a final exam and then eventually take a final exam. So we'll probably meet 3 or 4 times here in a row, Tuesday, Thursday, and then we won't meet for a week or 2, and then we'll have a final exam review, and that'll be the end of the class. So my goal is really just to get you guys through the family map project. Before we start, I guess I want to field any questions you guys might have. I know through Zoom there's a way you can raise your hand. If you want to virtually raise your hand, I'll try to answer your question that way, or you can go into the chat. There's a chat feature, and you can text me a message or chat me a message down there if you want to ask me a question that way. So does anybody have any questions before we start? Okay, I don't see any questions yet, so I'll just keep going. And when you guys have a question, just try to get my attention either through the chat or through the hand raising thing. All right, my goal today is to talk about threads and asynchronous tasks in Android. And this topic really does relate heavily to your family map project. It does relate to user interface programming. At first, it might not be obvious why this relates, but I'll explain that in a minute. So my goal today is to teach you everything you need to know to finish the family map login assignment. So we changed the due date for the login assignment to next Wednesday, the 25th of March. And so my goal is to teach you how to do the threading for that, as well as talk about the architecture of that program. There's a number of pieces that you need to fit together to actually make that thing work. And so I'm going to explain all that today. All right, so the first thing I want to do is explain threads, because some of you know what threads are and some of you don't. And I need to explain what threads are. So threads is something that they learn about in CS 224, I believe. And the idea is this, that by default, a program only does one thing at a time. So when you're taught to program, like in CS 142, they teach you that a program starts executing in the main method, and then it runs through the main method, and when it returns from main, then the program's done. It terminates. And so that's kind of the single-threaded model that you're taught when you're a new programmer. But in reality, it's more complicated than that. And so what we want to do is talk about how things really work. And in reality, when you're writing software, oftentimes you would like to make your program do more than one thing at a time, if you can. And there's a lot of scenarios where it's really useful to have the program do multiple things in parallel or concurrently. For example, in your server project, you wrote a server, and that server is just sitting there receiving requests from clients. Well, what if a whole bunch of requests come into the server at the same time from different clients? The server doesn't really want to just process those requests one at a time. That takes too long. What it would rather do is process a whole bunch of requests at the same time in parallel. And so that's an example of when a multi-threaded program would be a good idea. But even in user interface programming, when you're writing programs that have a graphical interface, it's oftentimes useful to make your program do more than one thing at a time. For example, on this slide, it shows an example where the program starts in main on the left side, so you can see the main function over here, and it's running on a thread of its own. And the X, that just means the thread terminated. But you'll see here that this program actually does three things at once. So it does whatever's happening on the main thread, but it also creates a second thread to print a document. So you might imagine that if you print a document, that takes a while. And you don't want to sit there and wait for the whole document to print before you can keep using your application. You'd like to be able to keep doing your work while in the background the document's printing. And so to do that, you could create a background thread on which the printing work gets done. And then the main thread can just keep doing other things. Similarly, in this example, the main thread wants to also call a web API. So maybe it wants to, call a server and get some data or whatever it wants to do. And so it wants to make an HTTP request. It wants to call a web API on a remote server. And again, that's something that takes a while. Making the connection, sending the request, getting the response, all that stuff takes a while. And you'd rather not have your user interface freeze while that's going on. And so the idea here is you could create a background thread on which you call the web API, and then the program can be doing that in the background while other things are going on. Okay, so it looks like I got a question here. So the question is from Joseph. He says, when it enters a different thread, if it exits main while the other thread is still running, are the other threads deleted? And the answer is no in this case. So, and I tried to draw this picture. Well, I guess I didn't. But the idea is that if a program creates a whole bunch of threads that are running, the program will keep executing until the last thread finishes. So even if the main thread has finished and terminated, if there's other threads that are still running, that program will still keep going. And in fact, your server, for the Family Map server, was doing exactly that. I don't know if you noticed, but once your server created the HTTP server object and then told it to start, the main thread terminated right away. And it was only a background thread that was created by that HTTP server that kept that server program alive and going. So no, the main thread connects it, and the program will still keep running. Good question. All right. So we can create multiple threads to do multiple things at once. Okay, now the reason this works is because every thread that you create in your program has its own runtime stack. And so that's depicted here in this slide at the bottom. Every thread that you create has its own runtime stack. And as you know, the runtime stack is the mechanism that they use to keep track of where the program is at, what it's doing, to implement all the method calls involved. And so if we have multiple runtime stacks, that allows the program to do multiple different things at once, independently from one another. And yes, all these threads are running in the same process. They're sharing the same memory space, or the same address space, but they actually are running on their own runtime stacks, and so they can be doing different things at the same time. All right, let me know if you have a question, because this is new to some of you, probably. All right, so I actually want to show you an example of how this works, and I'm going to do it in Java for obvious reasons. So in Java, there's actually a class named thread. So if you want to write a program that creates extra threads, you can use this thread class to do it. And the way thread works is, what you can do is you can write a subclass of it. So in this case, we want to write a thread that calculates prime numbers. Well, I didn't want to do that. Somebody wanted to do that. And so what you do in this case is you can write a subclass of thread. So in this case, prime thread extends thread. And what you do is in your subclass, you override the run method. So the run method contains the code that will actually run on the new thread. So whatever you want to do on this new thread, you just stick it in the run method. So in this case, they initialize the prime thread with a minimum number that they want to start calculating primes at. And then, although they don't show the code here, when the thread calls run, it'll just calculate those primes. And so the way you would use this class is in your program, you would just create a prime thread object, initialize it, and then just call start. And so when you call start, that would cause a new thread to be created, and the code that's in the run method on that thread would run on the new thread. And so at that point, the program would be doing at least two things in parallel. And you can just keep doing that for all the threads you want to create. You just create a thread object, tell it to start, and boom, it goes. All right, so I want to show you a more specific example of that. So we got a question here from Nathan. He says, is start a method inherited from thread then? Yes, the start method is inherited from thread. So every thread has a start method on it, and it is inherited. Now the other method that's inherited is the run method. Of course, that's the method that you would override to put the code on that thread. You wouldn't actually override start though. But yeah, both of those things are inherited. Good question. All right, now I'm going to show you another example of this and kind of run it for you. So I made an example of my own. So I created this thread class called counting thread. And what this thread class will do is it will start at a certain value and it will just count up or down to another value given the increment that you give it. So this thread object would start counting at 0, and it would count up to 50, and it would count by 1. That's why I call it the up thread. I also create a down thread here. It starts counting at 50. It counts down to 0 by increments of -1. So I just create myself a couple of threads here, and then I just start them both, and I just let them run. And what you'll see is the output from those two threads interleaving with each other in a relatively arbitrary way. So let's run that. Well, actually, let me show you what it looks like when it runs first, and then we'll look at the code. So when I run this program, the two threads run in parallel, and you'll see that first down goes first for whatever reason, and then up gets a turn, and then down goes a couple of times, and up goes. And so you can see that the execution of these two threads is interleaved in real time so that they are in fact running concurrently. But the thing is every time you run this program, these activities will interleave differently. And so the output is different every time. And so this is an example of a program that has non-deterministic output. Every time you run it, it outputs something different, which can be bad if you're trying to test software. So if we run it again, let's see what we get. Well, down goes 5 times, and then up goes a bunch of times, et cetera, et cetera. So you can kind of see how that goes. So that's just a simple example of two threads running in parallel. Now let's look at the code for that. So I create a counting thread. It extends the thread class. And when I initialize it, I give a name, I give a start value, stop value, and an increment. And just store those in variables. And then in the run method, it does exactly what you would expect. It just has a little loop that goes from start to stop using increment, and this prints out each value as it goes. All right. All right, we got a question. Caleb, if your main thread needs to return data from the thread later on, is there a way to pause until the thread finishes? Yeah, so there's a whole lot here I'm not telling you about how threads work, but there's a join method on the thread class, for example. So if the main thread wanted to call join on the other thread, that would cause the main thread to block until the other thread finishes. So there's a bunch of methods that you can call on a thread that allow you to control the different threads, and they can synchronize with each other and interact with each other in different ways. And so that the join method on the thread class would do what you want to do there. It allows one thread to wait until another thread finishes, basically. Okay, another question from Dallin, is this example online? And the answer is, as of yesterday, yes. No, actually, this was up there before. Yeah, it's on my lecture notes. It's in the, I think it's lecture 20. It's, I think it's called AsyncTask or something like that. So this example is online. Everything I'm going to show you today is online, by the way. All right, let's keep going. Now the big question is, what in the world does this have to do with Android programming? Well, threaded programming is useful on any platform, and so you can create threads on Android for all the same reasons you would create them anywhere else. But I actually want to talk about this for a very specific reason that relates to user interface programming, which is kind of the focus of this current project. So in a program that has a graphical interface, the framework or the library or whatever you're using to build your interface, in this case we're using the Android libraries to build our interface. But a user interface library, almost universally, I think I've never seen a counterexample to this. Every library that I've ever seen has what's called the UI thread or user interface thread. And a user interface thread is a special thread that does all the user interface processing. So even though your program might have a whole bunch of threads running inside of it, there's only one thread on which all the user interface updates and actions occur. And so the system, the user interface library or whatever you're using, would create a special thread in the background called the UI thread. And this slide depicts that. So in this case, your program would start running in the main method here. But when you initialize your user interface in that process, the platform or library would create a UI thread in the background. And what this UI thread does is it sits there in a loop. And that loop processes what's called the event queue. So what happens is every time the user performs an action in the user interface, whether it be a gesture or a mouse click or a keyboard press or whatever it might be, those events go into a queue. And so you can see my nice little event queue here. And so when a user produces input to the program, each input is turned into an event object, which goes into a queue. And then the user interface thread just sits there in a loop. And what it does is at the top of the loop, it grabs the next event from the queue, and then it takes that event and it calls the listener on the widget object that event belongs to. And the UI thread just calls the listener method and passes it the event that came out of the queue. And so this is how the events get passed to your listeners, and that's how the whole user interface kind of runs. And of course, the listeners do whatever they do to run the application logic. Okay, looks like we got a question from Christopher. He says, is the event queue a priority queue? Typically not. Typically it's just first in, first out. There are some cases where you might be able to put something really important at the front of the queue. So there's some exceptions to that, but usually it's just first in, first out. So events get processed in order of the time that they occurred. Good question. All right, now, so what does this really mean? So there's a couple of things. So first, we've talked about how all the listeners get called on the UI thread, which is great. But the other thing that comes out of this is that you need to write your program such that the UI thread never blocks. For example, let's suppose I have a listener in my user interface and it gets called with an event. Well, what if my listener takes a really long time to run? I'm doing a whole bunch of stuff in there, like I'm printing documents, I'm calling web APIs, I'm doing all this stuff inside that listener. Well, if my listener takes a long time to run, well, what does that mean for the UI thread? That means the UI thread is now blocked on my listener, and it's not able to process the other events that are in the queue. And so the whole user interface just comes to a grinding halt. It freezes. And most of you have seen this effect when you've used the program before and for some reason the program locked up or it froze and it wasn't responsive to your inputs. You're like, well, what the heck? What's going on? Well, usually for some reason the program has blocked the UI thread so that the events aren't being processed. And so one of the things you have to learn is that in a user interface program, if you have a listener that needs to do something that takes a long time, like call a web API or maybe access a database or whatever it might be, you might need to actually do that on a different thread. And so the way this works is the UI thread is processing all the UI events. It calls my listener at this point. And if my listener needs to do something that takes a long time, I don't want to do it on the UI thread because that'll freeze the UI. So what I need to do is create a background thread and do my long-running logic on a background thread. And that would allow the event thread to keep processing events while my work is happening on a background thread. And so this is just a basic concept of user interface programming, is that you just can't block the UI thread. It's like antisocial. It's just wrong. You can't do it. Now, in our case, why are we talking about this? Well, in Family Map, your client needs to call your server using HTTP requests. And so you got to make sure that when you make those web requests, you don't do it on the UI thread. You need to create a background thread and do it there. Now, is this concept specific to Android? Not at all. This is a concept that comes up in every environment I've ever been in, and that's quite a few. For example, in JavaScript, if you've ever been a web programmer, in JavaScript, they go to incredible lengths to make sure that the UI thread is never blocked. So you get into all these funky asynchronous programming models in JavaScript, and the whole purpose of that programming model is to make sure that the background thread or the UI thread doesn't get blocked. And because JavaScript is largely a single-threaded environment, you've only got one thread, and you've got to make darn sure you never block it. And so it just gets ugly from that point. So this is a concept that applies in Microsoft Windows, web programming, mobile programming, everywhere. Thou shalt not block the UI thread. Now, the other thing that the UI thread is for is that in your widget tree, so every activity has a tree of widgets, right, that we can call methods on. Of course, these listeners are methods on our widgets as well, but there's other methods you can call on your widgets, like set text or set background color. There's lots of methods on a widget object that you can call. But the rule is that anytime you call a method on a widget object, you have to call that method from the UI thread. You're not allowed to call, for example, a method from a background thread on a UI widget. Like you couldn't say set text on a text field from a background thread. That wouldn't work. So the idea is that user interface programming is typically intended to be a single-threaded activity where there's only one thread. Everything related to the UI happens on that thread. If you're going to call a method on a UI object, you've got to do it from the UI thread. The event listeners are always called from the UI thread. And again, thou shalt not ever block the UI thread. Okay, we got another question, a couple of questions. From Corey. He says, is it good practice to have every listener start a new thread? No, that would not be a good practice. Because when you start a thread, there is a certain amount of startup cost involved there. And you wouldn't want to do that unless it's necessary. So the only time I would create a thread in a listener is if the listener is going to run for more than a few, certainly if it's going to run a number of seconds, you'd want to create a new thread. But if it's going to run even more than a few milliseconds, probably, I'd probably create a background thread. Really the metric is if it's going to make the UI look sluggish and look like it's freezing up, then I need to create a background thread. Otherwise, don't bother. All right, another question. Is that why I had an issue with network on main thread exception, which gets thrown when I try to register a new user through the app? Yes, this is Android telling you to not block the UI thread. So you were probably trying to call your server on the UI thread, and Android is it's saying no, you can't. I'm not going to let you. Guess they're pretty strict about that. A lot of environments will let you block the UI thread if you want, but it's not a good idea. But it looks like Android's kind of a, it's a heavy-handed master in this case. Doesn't even let you do it. Good questions. So I'm going to segue into how do we, in the Android environment, create background threads? How do we avoid blocking the UI thread? All right, so in Android, because it supports Java, you can use the Java thread class if you want on the Android. I mean, you can just do normal Java threaded programming if you wish. But Android actually provides some other classes that are actually better to use on Android if your background threads need to interact with the user interface at all. So again, we said a background thread's not allowed to actually interact with the user interface at all. So what if you do have a background thread that needs to display things on the screen or talk to the user somehow? And this is a common situation because usually if you're doing something in the background that takes a long time, usually you want to give your user some status updates or some progress updates, like progress bars or icons that sit there and spin, or whatever visual cues you want to give your user that we're working on it, we're busy. That progress update comes from the background thread because the background thread is the one that is doing whatever's happening in the background. It knows what the status is. So how do we, from a background thread, actually update the user interface to display status? And so in Android, they provide a class called AsyncTask, which is really well integrated with the user interface subsystem on Android. And they give you some mechanisms that actually allow your background thread to indirectly interact with the user interface. And so that's the whole point here of why we're using AsyncTask instead of thread, is that it lets us update the UI in important ways. Now for this section, I'm going to go through a code example that's on the website in my lecture notes. It's called Async Web Access. I've actually got two versions of this example. One is slightly more sophisticated than the other, but I'm going to start with the simpler one first, and then I'm going to show you the right way to do it in my mind. And you can use either approach you want in your project. We will not judge you. All right, so I have an amazing app. Now, the problem I'm going to have here is that I need to bring up my Android emulator. I guess that's not a problem for you. All right. So I'm going to run my app. Can you guys see that? Would somebody just chat me and tell me if you can see that come up on the emulator? Yes. All right, we got it. Good deal. All right, so what I'm going to do, what this program does is it actually just, when I click the download button, what it does is it downloads 3 web pages in the background. And it has a progress bar up here. And so every time one of the pages gets downloaded, the progress bar should advance by 1/3. Or if I had 5 pages I was downloading, it would advance in fifths, right? So, and the other thing it shows here is how many bytes of data were downloaded total when I was downloading these web pages. So if I click download here, it just you can kind of just see it advance. So I downloaded 182K. It's so fast you can hardly even see it. My code tends to be extremely fast. Sorry, guys. All right, so now this obviously has to happen in the background because the user clicks the button and that happens on the UI thread. So when I click the button, that causes a click event to go to the listener on that button, and then the button needs to download those web pages, but it can't do it on the UI thread because it just takes too long. Now the problem is in this example, it actually happens so fast that it's not a big problem, but let's assume that the downloading took longer than this. Then it would be a big problem to do that on the UI thread. And so what we have to do is just kind of see how to do that in the background. So first thing, if we look at the XML layout file for this activity, you'll see a relative layout here, which we'll talk about soon. But inside the layout, I've got a progress bar widget. And so that's the little progress bar up here. I've got a text view, which displays the total number of bytes that have been downloaded. I've got a button. So I've got my button there. So those are all the widgets that I've got in this activity. So if I go to the main activity, you can see, I've got my widget variables inside my activity. And then in my onCreate method, I wire up my widgets. So I call the super onCreate, I inflate my widget tree, and then I wire up the widgets. So in this case, I get a pointer to the progress bar and the text view and the button, and then I put a click listener on the button. And when the button gets clicked, it calls this download button click method. And after I configure my widgets, then I just reset all the views. So I just set the progress to 0 and I set the total size counter to empty. Okay, so that process initialized my UI. And now when the button gets clicked by the user, this is what happens. So I create a download task. Now Android calls these things async tasks. Java calls them threads. Same thing, really. So rather than saying thread, I call it a task. Now download task is a class that I wrote, and I'll show you that next. But the notion is that once I've created my task object, I can tell it to execute. So in Java, you tell the thread to start. Well, in Android, you tell the task to execute. Same thing. That's the point where the thread, the background thread, actually gets created and runs. Let's see, I've lost my chat window. I need to dig it up here. Figure out if anybody's asking me a question. All right, we have a question. Okay, Caleb says, where is the code for the UI thread? That would be part of the Android platform. So that's not code that you would normally see. But if you drill down into the source code for the Android platform, you would be able to find the code for the UI thread, and it would have the event loop processing and all that stuff. I've never actually dug into Android to find that actual code, but I've done that on other systems before, but you can find it if you work at it. Good question. Then Dallin says, what thread is the main activity running on? So the main activity, every activity in Android runs on the UI thread. So we said before there's a main thread that initializes your program. But once the program's up and running, the main thread is probably finished at that point. And from then on, all the processing of the user interface is done on the UI thread. So even the main activity, even though it's called main, would run on the UI thread as well. All right, good questions. Okay, so back to this code. So I create a download task, I tell it to execute. Now, the way I've written this task is when you tell it to execute, what you do is you pass it a list of URLs that you want it to download. Now, in this case, I just passed it 3 URLs. I could have passed it 1 or 10 or even none, I guess. So it's written so you can pass it an arbitrary list of URLs. And it'll just download whatever you give it, and then add up the bytes. Okay, so that's how you create the task, that's how you run the task, but let's look at the task class itself. And so this is what you're going to be doing, like for logging in. When somebody clicks the sign in button in Family Map, the click listener for the login or sign in button will create a task object like this, and it'll run it in the background. And so you'll actually call your server in the background from one of these tasks. I think this code example will be really helpful when you're working on the Family Map. Okay, you'll notice here that download task inherits from the AsyncTask class. AsyncTask is a generic class, so it's actually got, don't do that. It's got 3 generic parameters on it. So these are class names or data types. The idea is you can pass in whatever classes you want for these 3 parameters. But in my case, I passed in URL because in my do in background method, I have URLs that I'm passing in. So this parameter up here matches the parameter type on the do in background method. And then you'll notice here that the 3rd parameter here matches the return value from do in background. So you can customize this do in background method, use whatever data types you want it to use.
Wow.
I just happen to be using URLs and longs. And I'll explain this other parameter in a second, but you'll see how it works. Okay, so in my download task class, what I will do is I'll override the do in background method. Now in Java, on the thread class, you would override the run method. Well, with an async task, you would override the do in background method. It's the same idea. This is the code that will run on the background thread. And you can see here that whatever parameters I passed to the execute method. And remember that when I call execute here, I'm running on the main thread. I'm running on the UI thread out here. So when I call execute, I'm running on the UI thread. But whatever values I pass for parameters in here, it passes to my do in background method down here. So that's how you pass parameters into your task, is just by passing those parameters to execute. Then Android passes those through to the do in background method. Now, one thing that's kind of weird about this do in background method is it uses some syntax you might not be familiar with. This ... thing. That's actual real Java syntax there. And the ... syntax is how you write what's called a variadic method. A variadic method is a method that lets you pass in any number of parameters to it. So you can pass in 0, 1, 2 parameters, whatever number of parameters you want to pass. You can pass in any number you want. And so what this syntax says is that this method accepts any number of URL objects. And the parameter's name is URLs. And so inside the do in background method, the URLs parameter is just treated like an array. So you can see right here, I'm just indexing into the URLs array. So this is really just an array. And this is just some funky syntax that makes it really easy to pass in an array of values that's of arbitrary length. And you'll see up here, I passed in 3 URLs. I didn't even have to put them in an array. Java converts that to an array for me. And so that's what that syntax means.
Publish progress. Oh. What? That's so cool.
All right, somebody needs to mute. Who needs to mute? I've got this all-powerful mute all button. It's kind of cool. Ha! All right. So this is the code that's going to run in the background. You'll notice all I do here is I create an HTTP client object. The HTTP client object in this example is analogous to the server proxy class that you're going to write. So if you look at my HTTP client, it's really just a simple class. It's got a get URL method on it. You give it a URL as a parameter, and it downloads the document at that URL and returns the contents of the document. But internally, it uses the HTTP URL connection. So this is analogous to the server proxy in your project. A lot of times, students will ask me, where's the server proxy in this example? And so this is my answer. The server proxy is the HTTP client. Okay, so James asked a question a minute ago back on the doing background method. This question was on the doing background method. Could you actually call this method with an array rather than have Java convert it to an array for you? So up here I called it without an array. And the question is, could you call it with an array if you wanted? And the answer is yes, you could, which is kind of cool. All right, so what does this background method do? It creates an HTTP client, then it just goes into a little loop here and downloads all the URLs that we gave it. It has an accumulator variable that calculates the total number of bytes we download. And so it goes around the loop, and for each URL that we passed in, we download the URL, and we get the document back. And then I just calculate the length of the document and add that to the total size. So that's simple stuff. And then I calculate my progress. So I want to calculate what percentage complete the download process is. So if I just downloaded the first of 3 documents, it should come out to be 33%. And so every time I finish downloading the document, I calculate what percentage complete are we now. And so here's a little bit of logic that calculates that. How complete are we? I cheat here to make sure it goes to 100 at the end, no matter what. Now, the reason I'm calculating the percent complete is so I can update the progress bar. I want to advance the progress bar and show the user how far done we are. Now, I've got a problem at this point, though. Having calculated the progress percentage, what's the problem? Think about that. What's the problem that I've got? I want to tell the user what percentage complete we are, which means I need to update the progress bar. But here I am running on a background thread. So am I allowed to call set progress on the progress bar? And the answer is no. I can't do that from here because I'm on the wrong thread. I'm not running on the UI thread right now. So I can't update the progress bar from here. Bummer. So this is where AsyncTask comes to the rescue. So if you'll notice here, I inherit from AsyncTask. One of the methods that I inherit from AsyncTask is this method called publish progress. And so the idea here is that if you ever want to publish a progress update to the user interface, you can just call publish progress from the background thread. And you can pass in whatever progress value you calculated. So in my case, maybe it's 33 or 66% or whatever. So once I've calculated the progress value, then I can pass that progress value to Android. So I call publish progress. So I might be saying, Android, we are 33% complete. But I'm running on the background thread and I need your help to update the progress bar. So I call publish progress. This progress value goes to Android. And then what Android does when you call publish progress is it turns right back around and it calls the onProgress update method on your async task. So I call publish progress on Android, and then Android turns around and calls onProgress update on my async task class. Except when Android calls this method, it calls it on the UI thread. So this represents a thread switch. When I call publish progress, that's a way of switching from the background thread to the UI thread. So I call publish progress, Android calls me, and he passes me the same value I passed him. So if I pass 33 here, he's going to pass me 33 there. And so all we've done is we've performed a thread switch. And then from the thread switch, I can actually update the progress bar. So I can say progress bar dot set progress, 33 or whatever the number is. So progress bar here, as you'll recall, is the widget up here that we initialized in our main activity. So this is how you can interact with the user interface from a background thread, is to use the AsyncTask. Call publish progress, thread switch occurs, and then from this method you can call methods on the widgets. Okay, another question. Does the async task wait for on progress update to finish before continuing execution? And the answer to that would be no. So this background thread will not wait. It'll just keep on trucking. So this publish progress, it's a fire and forget. I notify the other thread, or I notify Android that my progress has changed, and then I just keep going. And this method will get called as soon as Android can make that happen. What they'll probably do is put an event in the event queue that calls this on progress update, so that my on progress update method will get called in its turn, but all the other events in the event queue will probably precede it. So the background thread doesn't worry about that. He just keeps going. Okay, another another question, Shad. How would a breakpoint work in a multi-thread program? Does it only stop the thread where the breakpoint is, or do all threads stop? Yeah, so when you have a multi-threaded programming, debugging gets ugly. So typically it only stops the thread you break on. Now, if you hit the pause button on your debugger, it'll stop all the threads. So that's usually what you end up doing in a lot of times in a multi-threaded situation, is you just hit the pause button on the debugger and it'll break all the threads all at the same time, and then you can look and see what's going on. But a breakpoint itself will only break one thread. So debugging multi-threaded programs gets a little dicey, but it's fun. It's better than having coronavirus, I guess. All right, let's see. Where were we? So one thing I wanted to point out is that my AsyncTask subclass that I wrote, this is actually a nested inner class. It's inside of the main activity. So out here we got main activity. Then nested inside main activity, we've got the download task class. Now, because download task is nested inside main activity, the nested class can access the variables and the methods of the outer class. So that's why this AsyncTask subclass can access progress bar and total size text view. So that's one advantage of nesting the AsyncTask class in your activities, that the task can access whatever it wants inside the activity, which can be good. But it can also be bad, and I'll show you how to do it differently in a second. All right, question, Chasten. Since we use the login and map fragments in our main activity, should we make any async tasks nested within the fragments themselves? The answer to that is maybe. If you want to put your async task inside your login fragment, you could. And that's one way to do it. It's probably the easiest way to do it is nest a login task inside your login fragment. And that's fine. But that kind of prevents you from reusing that task class elsewhere if you wanted to reuse it somewhere else. And so what I'm going to show you next is a variation on this example where the task is not nested inside the activity. So you can just choose. You can do it nested or not nested, whichever way you want to do it. And I'll show you how to do it both ways. So this is the nested version, obviously. Okay, so let's finish this workflow out here. So publish progress is the way we switch to the UI thread so we can update the UI. Now, the next thing that happens here is when this background thread is totally done, it returns the total number of bytes that we downloaded. And so that's the result of this doing background method, is the total number of bytes that we downloaded. So I return the total size. Now I want to display that number in the user interface. So again, I have the same problem. I want to take the total number of bytes that I've downloaded and I want to display that in the user interface. But the problem is, again, I'm still on the background thread and I still can't talk to the user interface from here. And so what I'm going to do in this case, once you're doing background method returns, it returns whatever value you want to return. What Android will do is when doing background returns, it will immediately turn around and call your onPostExecute method. So once the background thread finishes doing background returns, Android takes the return value from doing background and passes it to onPostExecute. So whatever value I returned here is going to get passed in here. And again, the onPostExecute method gets called on the UI thread. So again, a thread switch has occurred. And that allows me to do a final update of the UI after the background thread's done. And in this case, I go ahead and display the total number of bytes that were downloaded. And so really this download or this AsyncTask class, it's really all about making sure that you're calling your UI objects from the right thread. And it's just super handy to have it, because if you were just using regular Java threads, you wouldn't really have a good mechanism for calling code on the UI thread like this. And so this is really quite necessary to make stuff work. Okay. I guess that's pretty much it on that. I mean, if I go out here to the main, yeah, there's really nothing else. That's the whole darn thing. All right, any questions on that before I move on to an upgraded version of this? Okay, so question from Caleb. So onPostExecute is comparable to a .then function in JavaScript. Yeah, there's an analogy there. Is there anything comparable to catch? If you get an error, no, you're pretty much, error handling is going to be up to you. In this case, I can't think of anything that's analogous to catch on a promise. But I mean, you could keep track of that in here because you're actually writing all the code. So if an exception gets thrown by anything, you're going to be able to know that with a catch. And then you could pass that information either to the on progress update or the onPostExecute. I mean, this is your code in the background thread. So if something goes wrong, you can propagate that information so that these methods know it, and then they can display the error messages. For example, you could have an extra variable inside your download task, like it's an error. You know, so if an error occurs, then these methods that are running on the UI thread could see that and they could display the error. But they don't have a catch directly. Jared asks, does the do in background need to have a specific name, or does onPostExecute catch when the end is reached no matter the name? So let me clarify that. So do in background is the name you have to use. So this is a method that we inherit from from AsyncTask. And this is the method that you have to, that's the name you have to use. This is an override. I should tag it override. And the same goes for these other methods as well. Those names are defined by the superclass, and you have to name them just like that. The only control they give you is the parameter types. See these three parameters? You'll see those are my, my parameter type here, my return value type there, and my parameter type here. And you can customize those to your heart's content. But the method names are fixed. Good questions. All right, let's move on to another example. Okay, so the next example is the same as the example I just did functionally. It does exactly the same thing. It's just the structure of the code is different. And so what I mean by that is, in the previous example, my download task class was nested inside the main activity. What if I didn't want to nest it? And there are some good reasons to not nest it. For example, the single responsibility principle. You could argue that whatever work that download task is doing, well, maybe that doesn't really belong in the main activity. Maybe it would be better to factor that out into a different file from a single responsibility perspective. The other argument for not nesting the task inside the activity is if you want to reuse it from multiple activities. If I nest the class in one activity, then I'm not going to be able to use it from other activities. And if I have something that needs to be reusable, I wouldn't want to nest it. Now, admittedly, we've simplified this project. We used to have an example of that in this project, but we took that out this semester just to simplify it a little bit. So in this project, this semester, if you wanted to nest your tasks inside your fragments, you could. But I think it's instructive to see what it would look like if you didn't nest it. So let's kind of look at that. So this is a version that doesn't nest the download task. So if you go through the main activity, it looks like it did before. It still creates a download task and executes it. But you'll notice that the download task code is not in that file. So I've moved the download task over here to a different file. Now the challenge is, once you move the task out of the activity, then that means the task class doesn't have access to the variables or methods of the activity class anymore, because it's not nested. So it can't see the progress bar widget or the text view widget. So the disadvantage of moving the task outside the activity is it can't see the widgets anymore, or it can't call the methods on the activity anymore. And that's the downside. So it's a trade-off, right? Like most things in software design are, you got trade-offs, and you just have to optimize what you care about the most. So the download task class is in its own file. Looks pretty similar to what it did before. It's got the do in background method that does all the same things. The only difference is actually in these two methods that get called on the UI thread by Android. On progress update, this is where I used to update the progress bar to show progress. And I can't do that anymore. I used to say progress bar.setProgress, but I can't do that because I don't have access to the progress bar variable anymore. Same here in onPostExecute. I used to, in the text view, I used to display the number of bytes we downloaded. I can't do that anymore because I can't see that widget anymore. And so the question is, if you don't nest the task inside your activity, how do you do UI updates? How do you do progress updates in the user interface? And so I'll show you how I did that. So what I did is I created an interface. It's a listener. So I treat this like a listener. So I created, inside the download task, there's an interface called listener. And it has an event method for every event that somebody might want to be notified about that might happen inside a download task. So whenever you do a download, there might be an error that occurs. So I might want to notify somebody that an error occurred. Or I might want to do a progress update. I want to tell them what percentage done we are. Or I might want to tell them when the download's complete and tell them how many bytes we downloaded. So this listener interface represents all the quote unquote events that might come out of this download task while it's running. So whoever creates the download task object, what they can do is they can pass in a listener. So whoever created the download task, and in our case, the creator of the download task would be the main activity. What the main activity can do would be to, as a parameter here, pass in a listener object, and we store that listener inside a variable. And then what happens is inside the download task, now that we've got this listener object, what we do is anytime we want to do a progress update, we just call the onProgressUpdate method on our listener. Or if we want to notify that the download's complete, tell them how many bytes we downloaded, we call that method on the listener. So what we've done here is rather than updating the widgets ourselves in the user interface, we've decoupled the task from the user interface, and we simply notify whoever created us that something interesting has occurred. It's like an event. And so now the task class is decoupled from the context in which it's being used. And so from a software design perspective, this is a nice form of decoupling. It keeps my classes more independent, more reusable. They don't know as much about each other. And so that's one of the nice things. So if I were to program this project, this is how I would do it. But I realize some people will feel less comfortable with this approach. Okay, looks like we got a parameter perhaps, or not a parameter, a question. Why do you set the listener to 1? Ha, it's L, sorry. Yeah, I shouldn't have done that. I think that was the letter L, so we already have an answer to that. Yeah, you're correct. Yeah, that's poor naming example on my part. You should never do that. Do as I say, not as I do. I'm not going to get a very good score on my code evaluation. Okay, another question. Also, where does that listener learn which widget to point to? Okay, so I'm going to show you the other side of this. So I hope you can see how the download task works. It creates a listener interface, and if you pass a listener, it will call your listener when interesting things happen. But to really see how this fits together, we need to look at the main activity, which is the creator of the task. So first thing in the main activity, you'll notice here that the main activity extends app-compat activity, but it also implements the download task listener interface. So in this case, I actually implement the listener interface on the main activity itself. Question, why is the listener interface nested instead of its own class? You could do it either way. It doesn't have to be nested. The reason I nested the listener interface inside the download task is because this listener interface is pretty tightly coupled to the download task. But if you think that need not be the case, then you don't need to nest it. In fact, that would be great if you didn't, actually. Okay, so notice that the main activity implements the listener interface. So if we go down here, let's see, when the download button gets clicked, we create the download task and execute it. But notice when we create the download task, what do we pass to it? We pass it a listener object, which in this case is the main activity. So that's why we're passing in this. So what that means is that while the download is running, anytime anything interesting happens, the download task is going to call a method on the main activity. And then if you go down here, this is the implementation of the listener interface on the main activity. So on error, I didn't put anything in there, but I could have. Okay, so if on progress update gets called, what's the main activity going to do? Well, he's going to do the same thing that the download task used to do. He's just going to set progress on the progress bar. He's the only one that can do that because he's the only one that has access to his widgets internally. So the download task is calling the main activity and saying, hey, would you update your progress bar? And then the same thing on the download complete. The download task calls that when the download's done, and then the main activity would go ahead and update the text view. So we've decoupled the task from the main activity. It's easier to couple them if you're in a hurry and just want to get a project done, but if you want to structure your code a little better in a way that might last the test of, or stand the test of time a little better, this approach is probably slightly superior, I would say. All right, question. Where will this code be so we can compare the implementation that involves a nested task and the one that doesn't? So if we go to the lecture notes, let me just show you where this all is. So if I go to the website here, I go to the lecture notes, go down to lecture 20. You'll see basically all the things I showed you earlier. But you also see in the code folder that there's two projects. There's async web access, and then there's async web access with listener. So those are the two different versions of the project. You can either browse those online here, you want to just drill down into the code, or you can download the zip files and actually compile and run them in Android Studio if you want. Okay, let's see. Follow-up question from Carter. Why is the listener interface overriding those methods? Is it inheriting from something else? Okay, so if I go to the listener interface, I don't think it overrides those, does it? So these are not overrides. So there's no overrides in here, but in the main activity, those are overrides because it is implementing the interface. So that's why those are overrides. Anytime you implement an interface method, you're doing an override. Okay, from down, in this way, isn't the background thread, the download task, calling a method on listener, which is in the UI thread? So objects are not in threads. Method calls are in threads. Let me explain that. So in this case, you'll notice that the listener methods are being called from onProgressUpdate and from onPostExecute. By definition, these two methods are being called by Android on the UI thread. So if these methods are being called on the UI thread, that means any method I call from here is also being called on the UI thread. So the way to think of it is method calls are running on a particular thread. I can run the same method on different threads. It just depends on where I call it from. So objects don't run on threads, rather method calls run on threads. We'll think of it that way. Okay, Carter says, sorry, I'm referring to the overrides at the bottom of main activity. Yeah, let's go back to that over here. You're talking about these ones? Yeah. So why is that an override? Well, if we look up here, I'm doing some inheritance, right? There's actually two kinds of inheritance going on here. One is implementation inheritance. So I'm inheriting methods from the superclass here, and I could override those clearly. But the other thing I'm inheriting is methods from here. I'm inheriting methods from the listener interface. Now, the interface itself doesn't provide any default method bodies or anything like that, so I'm not really inheriting any code. But because this is an example of inheritance, if I implement that interface method, I am doing an override. And so that's why this override annotation is appropriate. When you put an override annotation on there, what you're really saying is, compiler, I think I'm implementing a method that I inherited from somewhere, either an interface or a class. And I want you to make sure that that's true. I want you to go and check and make sure that I'm overriding something that I inherited. Because if that's not true, then I have a bug. I want you to tell me that. Yeah, right. Carter's got it. That's good. All right. So I think that's pretty much what I wanted to show you here. All I really want to show you, how do you unnest the task? And this turns out to be a good approach, as I'll show you in a second. Now this lecture might go slightly longer. It won't go very much longer, but I might have 10 minutes to go rather than 5. But I'm going to keep going because I want to finish out the last details here. And of course, if you want to drop off, you can do that. Of course, I wouldn't. All right, let's. Okay, so the last thing I want to talk about today is the design or the architecture for the family map login. Because like I promised, I want to make sure that you leave here with everything you need to finish that assignment. And so I tried to draw a diagram that shows you how all the pieces fit together. And so clearly we have a main activity in family map. And as we've discussed before, the main activity will display either a login fragment or a map fragment, depending on whether the user's logged in or not. So one of the things we're trying to learn how to do here is how does the main activity know when to switch the fragments? Well, obviously it needs to switch the fragments when the user logs in or logs out. So the question really is how does the main activity know when the user logs in or logs out? And you might think, well, he just knows. Well, actually he doesn't know, because all that logic is occurring elsewhere. For example, all the login functionalities in the login fragment. And so the main activity doesn't have any visibility into what's going on in the in the login fragment. So he doesn't know when the user logs in. So the structure looks like this. The main activity contains a login fragment, and then when the user clicks login or sign in, the login fragment creates a login async task that will actually call the server on a background thread. And so that's actually would happen inside this async task, is he would use the server proxy, he would call login on the server, and hopefully that would work. But if it didn't, the async task would need to notify the fragment that the login failed. And so that's what these methods over here represent, would be callback methods, or the listener interface that we just looked at in the other example. You could easily make a listener interface that had these two methods on it as well. So on login failed, on login succeeded. And so whatever happens down in here when we try to log in, we're going to need to tell the login fragment what happened. Either it failed or it succeeded, one or the other. Now, of course, once the user logs in, then we want to go to the server and fetch all the data for the user's family tree, right? Get all the people and all the events. So this async task would do more than just log in, perhaps. It would also fetch the data from the server. But ultimately, that entire process is either going to work or it's not. And we would need to call a method on the login fragment from the task and say, hey, it either worked or it didn't. Which is great. So inside your async task here, if you wanted to, you could define a listener interface that looked like this. And then the login fragment could implement that interface and then pass himself in as the listener on the async task, so he gets notified when interesting things occur. Now here's the interesting part though. Let's say the async task notifies the fragment when login succeeds or fails. That's awesome, but who is it that really needs to know whether login failed or succeeded? It's actually the main activity. So you could have another level of notification here. So the main activity could also be a listener, and he could attach himself as a listener on the fragment. And so when the task tells the fragment what happened, then the fragment could turn around and tell the main activity what happened. And so that's the way we could notify everybody who cares of the status of the user login. Did it work or not? And then everybody can respond to that however they want. And the beauty of that is that the async task, he doesn't have a clue. He's like, I don't know who's listening. I don't know who created me. I'll tell them what's going on. And then the same for the login fragment. He doesn't have to know what kind of activity he's inside of. He would just notify whatever activity he's in when login fails or succeeds. So this is a really common and important problem in user interface programming, is how do the different pieces of the user interface notify each other when interesting things happen? And so this is something we need to grapple with here in Family Maps. Okay, Caleb says, would the login fragment also use a different register async task if the user clicks sign up instead of sign in? It could. So the question is, would you do login, would you do sign in and register from the same task, or would you create two different tasks? One that does sign in, one that does register. And I would just leave that up to you to decide. From a single responsibility principle perspective, I would want to make them different. But you'll also notice that the code inside of them is so similar that you're like, man, I don't know if I need 2 different classes for that. They're almost identical. It's just one of them calls login, the other one calls register. They both need to download the data from the server. So you might, it's easily arguable that you'd make that 1 class instead of 2. And then we have a question from James, says, would register be a subclass? That's a good implementation. You definitely could maybe use some inheritance there to share the code that's common between those 2 tasks, but have them each be separate classes. So you could have a base class that has the commonality between them, and then you'd have 2 subclasses, login task, register task. That would be a good design. That would be a good design. Good questions. Okay, so this picture shows the map fragment over here as part of the picture, but you don't have to actually implement a login or a map fragment for the login assignment. I just put it here for completeness because I think the picture makes more sense with it there. Because really the main reason we're notifying the main activity that the login has succeeded or failed is so that we can either display an error message or we can swap the fragments. In either case, you're going to do something in the user interface to respond. It may just be a toast, or it may be, let's switch to the map fragment. But that notification is going to be important. And that's a part where a lot of people get stuck. When they get down into the bowels of the project, they're like, oh, wait a minute. You know, I've logged in here, but I don't know how to tell the main activity that. And so I'm just trying to prepare you for that eventuality. All right, so that's pretty much what I had to share today. Does anybody have any follow-up questions here? See, Jared, if we separate async tasks into their own class, instead of nesting them, and we have a login interface and a map interface, can main activity implement both of those? And the answer is yes. A class can implement as many interfaces as you want. And so the main activity could implement multiple listener interfaces if it needed to. Certainly. Where will this lecture recording be for us to access? Shad asks. So I'm putting the links to these lecture videos on the schedule page on the website. So if you go to, where is it? If you go to the class schedule, you can see here we have links. Here's my link for the fragment discussion. Dr. Wilkerson has his. Here's Dr. Wilkerson's link to his discussion that we just had. So I'll put mine right there with his. And if you don't like mine, you can always watch his, or vice versa. And yeah, I think it'll be right there. Other questions? Is everybody done? Everybody happy? All right. Well, thanks for being here. We'll meet again on Tuesday at 1:35, and we'll have another scintillating discussion about something. And I do wish you guys well. I know it's stressful right now, and so I'm praying for you. And you can expect an unusual level of compassion and leniency as we move through the course. So we'll see you next time. Thanks.